So we've got two topics that we want to discuss today, and the first one is friction. So our idea for friction is that it's a force that happens between two surfaces. So if you've got an object on a surface, then if the object is moving, or someone's attempting to move it, say to the right, and we'll label that force P for pushing, friction is going to attempt to oppose that. So that's fact number one. So friction opposes motion. We also notice, just from our everyday experience, that it actually takes more effort to get something started moving than it does to keep it moving. Right? So anyone who's ever moved a heavy piece of furniture has experience with that, for sure. So we make a distinction between kinetic friction, which is the friction that opposes movement, and static friction, which is the kind of friction that a surface will apply when something's not moving yet, but you're trying to get it moving. Third, the amount of friction that we get is proportional to the normal force that the surface is exerting on the object. And then we throw in this coefficient of friction, which is just a fudge factor to say that not all surfaces and materials behave the same. And in fact, there are engineers who spend their entire careers just measuring coefficients of friction between various surfaces. And if you go online, you can get some very specific lists. Personally, I like Engineering Toolbox. But there's going to be an abbreviated list on Wikipedia, or if you just Google what's the coefficient of friction between, say, wood and steel, you'll get some reasonable answer. Yeah, your book has a list of a few too. But remember, coefficients of friction are incredibly material specific. So you want to look up the best number that you can.
We get one on the test. Will you just tell us what the coefficient is?
Not necessarily, but I will make it a common enough material that you can Google it in like 3 seconds.
Okay.
Fourth thing we want to realize is that if we use this formula to calculate how much static friction we can get, that's a max, right? So if, for example, we have a 10 kilogram object and mu is equal to 0.5, we can apply Newton's second law. Say, well, sum of forces in the y direction is N minus mg which is zero, which is going to sum to 0 because the object isn't moving in the y direction. Can you label number 4? I'm not sure what you mean, Letitia.
I just mean as in what are they? I know that's friction. I don't know what's that subscript.
Yeah. So this is the coefficient of friction. More specifically, the coefficient of static friction. The N is the normal force. And this is the frictional force. Okay, so with that consideration out of the way, in this very simple box on a surface diagram that we have here, the normal force is equal to the weight. Therefore, we would expect the static frictional force to be like 50 newtons. And when we say that it's a max, what we mean is that the frictional force isn't going to produce 50 newtons of resistance unless you're pushing on it with 50 newtons of force. Right? If you push on it with only 10 newtons of force, then the thing isn't going to move. Right? So friction is only generating 10 newtons of force back. Right? So if P equals 10, then friction can only equal 10. Does that make sense to everybody? All right. You're going to... I'm sorry?
What does the Fy thing mean? Next to the summation sign?
Yeah.
What is the Fy?
Forces in the y direction.
Oh, okay.
Where did that 100 come from? The one that's like X,
yeah. So I was a little sloppy about this. I meant to say that the mass is 10 kilograms. There we go. So the weight is then 100 newtons.
Okay, thank you.
All right, so this is the idea behind friction. You're going to do a lab focused on this, on measuring the coefficient of friction of wood on wood. I think next week. So I'd like to do a full analysis of what I call one of the basic toy problems of mechanics. Right? We've got a few different toy problems that we turn to, and one of the ones that we'll turn to again and again is a box on a ramp. And it's not because we frequently encounter boxes on ramps in real life, but we will encounter situations that are basically a box on a ramp all the time. All right, so this ramp has friction. What we are going to say is that this box is at equilibrium, right? So the velocity of this box is 0 and its acceleration is 0. So this box is at rest on the ramp. This is one of the situations you're going to be examining in your lab. Let's draw the forces affecting this box. What forces what do we expect to be affecting our box here? Weight, friction, normal. That's good. That's everything. So weight points straight down. Friction and normal are a little bit more complicated. Normal, the normal force, and remember normal is a fancy, like old-fashioned word for perpendicular. So normal forces are always perpendicular to the surface exerting them. So normal force is going to go like so. Actually, pretend I drew that as a straight line. William, yes, this is being recorded. mg is mass times gravity. Yes. So that, which is the weight of the object. Now the weight of this object is going to tend to pull it down the ramp, and so that tells us that friction has got to be pushing up the ramp. All right. So there's step one. We've drawn a picture of this problem. Is normal always perpendicular to friction? That's an excellent question, Jasmine, and the answer is yes. So normal forces will always be perpendicular to the surface that they are on, and frictional forces will always be parallel to the surface that they are on. Is there friction if it's stationary? Yes. So if there was no friction, then the weight of the box would carry it down the hill. But we're saying that it's not being carried down the hill. And in fact, you know, from our own everyday experience, we know that it's possible to stand on a hill or a ramp and not fall down it. So the thing that lets us not fall down the hill is static friction. All right. The second thing we have to do in these problems is specify our coordinate system. Now, up till this point, we have almost always been saying that to the right is the positive x direction, and to the left is the, or sorry, to up is the positive y direction, and that's fine. You can definitely do, you can use that here as well. In fact, you can always use whatever coordinate system you want as long as you're consistent about keeping track of those directions. However, if we chose to the right as the positive x and up as the positive y, then when we went to break down vectors, we would see that mg is down, so that's exactly in the negative y direction. But then normal force and friction, we would have to break those down. So we'd have two vectors that we have to break down. There is another choice, though. And the choice that I like is to actually say that up the ramp is the positive x direction, and perpendicular to the ramp is the positive y direction. And with this choice of coordinates in hand, both the normal force and the friction are one component vectors, and we only have to break down the weight. So this is an effort-saving measure. When we're dealing with relatively simple problems like box on a ramp, it's not like a huge time saver. But when we get into more complex problems, this is definitely a trick you want to have up your sleeve. Like you want to be able to define the coordinate system in the way that forces you to break down the fewest number of vectors, just to simplify your own life. So let's break down these three vectors then. Given the definitions for the coordinates that we've just made, the normal force is only in the y direction. And the frictional force is only in the x direction. The weight's a little more complicated, but we know how to deal with that. And this actually seems like a really good time to do our group quiz. And it's going to be a short group quiz. We're going to take 10 minutes, maybe 8 minutes. And what I'd like you to do is just break down the weight vector in terms of the x and y coordinates we have here. So all you have to do is break down the weight vector x and y components, and that is it for our group quiz today. All right, so everyone grab a picture of this, and I'm going to open up the break rooms, the breakout sessions. Fill in these 2 question marks. That's it. So take a screenshot. Please no more than 8 people per breakout session. All right, enjoy.
Hi guys. How are you guys doing?
Sorry, folks. I had to step away for a moment. To join a breakout room, just open up the Participants tab and click Breakout Sessions.
Anything we know, the only equation we've been using is the sum of all forces equals to the mass times acceleration. And then we know that the weight equals to the gravity times mass, which will be downward, which will be the sum of forces in the y direction will be the normal of the surface pushing up on the object and the weight, so gravity pulling it down. And in the x direction, it's just going to be friction in the positive direction and weight in the negative. I just do not know how to put it in that coordinate way. What do you guys think?
That makes sense to me, but I also don't know how to get it to the coordinate.
Yeah, that's what I'm trying to figure out.
Did you get the picture? Whoever asked for it, I forgot.
Yeah, you're good. Thank you.
Sounds good.
Is this your final answer, people?
Yes. Is it wrong?
Should it not be?
So the negative y direction is down and to the right, going by the coordinate system that we've specified here. So something that's just down is not can't just be in the negative y direction.
Oh,
I think we have to make a
Sorry, I
triangle
don't get what that
from.
means.
It's all right. We're gonna
So,
go
like,
over it in the main session in a minute.
so it should be positive.
From the center point, I think I remember this kind of from when reading the chapter. From that center point, we need to draw like a line towards the right angle box, and then do a line.
25 would equal mg cosine of 25, or not 25, but theta, very similar to example 5.1. But I may be overthinking this. So just out of curiosity, how did you guys start to attack this problem?
Well, if you think about it, he didn't really give us any coordinates.
Cosine theta, and then for the y, it would be negative mg sine theta.
That's what I was thinking too.
You're so
Yeah,
close.
does that make sense? You saw I got that?
Yeah, there's like that triangle there, but I also see what he was saying with having to do with the normal force and this the friction, because the friction is our x, right?
Correct. Yeah.
Yeah. So our
Yeah.
so if our friction is our x,
Is everyone all done here? Is anyone alive here? All right, take one more minute, and then we're going to wrap this up.
Mai, do we need to request access from you?
Yeah, I just saw that. I'll share it.
Oh, you did? Okay, sorry. I
Yeah.
might send another one. Sorry about that.
No worries.
So